So we are going to continue talking about integration of rational functions. And we learned case 1, which was when we had P of x over Q of x, and Q of x can be broken into distinct linear factors, which are like this. Okay, distinct linear factors. Distinct linear. And in this case, I'm trying to completely go over it again, but this case, we had to do this. We wrote that P of x over Q of x was equal to these coefficients, A1 over each of these individual factors. And then we made a common denominator and then solved for these coefficients capital A1 up to AR. Oops. Okay. Now, as I promised on Friday, we're going to learn the other cases, which will be very, very similar, except it's a different form that we have to invoke at the first step. It's no longer the case that this algebraic fact is true. Now we're going to have a different fact to actually use. So case 2 is repeated linear factors. So in this case, we have that P of x over Q of x. Q of x has factors of the form ax plus b to some power, say r. When you have something like this, then you have to deal with it by adding a number of individual terms, which is, the number has to be r, depending on this power here, and the terms you add are as follows. So we need some coefficient a1 over the first power, ax plus b, some coefficient a2 over the second power, ax plus b squared, and so on, however many powers of this linear factor we have. And then if everything else is linear factors, then we write them with different coefficients above the distinct linear factors. Okay. We have x to the 3 minus x plus 1 over x squared, x minus 1 to the 3. Okay, firstly, is this proper or not? Is this a proper rational function? So it's a proper rational function. No need to do long division. We can apply our cases. And this is clearly case 2 because we have on the bottom repeated linear factors, right? Yeah? So tell me what linear factors you see repeated here. What are the linear factors we see repeated? Someone hasn't spoken yet. X minus 1 is the linear factor is repeated. Someone give me another one. Yeah, x itself is just a linear factor, right? So you have these two linear factors that are repeated, right? So according to this form, this thing can be written in the following way. And have, say, a1 over x plus a2 over x squared, deal with this guy. And then let's put b1 over x minus 1 b2 over x minus 2 squared plus b3 x minus 2 x minus 1 squared b3 b over x minus 1 to the power 3. Like this. This is following this form like this. Yeah? So this is the new algebraic fact that is just given to us. Okay? That something like this can be written in this form. And with this algebraic fact, we can then just proceed as before in trying to find all these coefficients. And it's exactly the same game as before. Once we find all these coefficients, then we will be able to integrate it. Okay? So, let's do an example of this. This is example 4. We have this thing. Okay, so what's the first step? What's the first step, people? It's improper, right? So we can't apply any of this stuff until we put it into the form of a polynomial plus a proper rational function. We have to do polynomial long division. We're going to skip that step. So by polynomial long division, this thing by polynomial division, this thing, if you carry it out, turns out to be this thing, x plus 1 plus 4x over x to the 3 minus x squared minus x plus 1. Okay, so this is by polynomial long division. Okay, so we can just deal with this thing because integrating this polynomial here is just a triviality, right? So now our problem reduces down to this, okay? And we're going to try and figure out what form this is in. And it turns out that we can factor the bottom x to the 3 minus x squared minus x plus 1. This turns out to be x minus 1, x squared minus 1, which will take you a bit of experimentation to find. I don't have a good suggestion as to how you see this, except that the examples you'll see in at least an exam will be pretty straightforward. You can rather quickly find out. Yeah. So if we look at this thing, then what do we have? Well, x squared minus 1 can be written as x minus 1, x plus 1. So we can write this as x minus 1 squared, x plus 1. And now we have a repeated linear form, this x minus 1, right? A repeated linear term, I should say. Yeah? So now this guy will be in the form of case 2. Yeah? Do you see what I mean, people? Give me a thumbs up if this is making sense. And do this gesture if something's unclear. So I've made a bigger screen as I can, but I'm still only seeing some of you, and some of you don't have your video on. So if you're doing this and I don't see you, then that's why I'm not responding. All right, anyone feel this way? Okay, so if not, then we just try and apply this stuff. So by this algebraic fact, this guy for x over this thing, x to the 3 minus x squared minus x plus 1, is in the form with these repeated factors. So it's going to have, this is the repeated guy, so we're going to write a over x minus 1, and let's put a b over x minus 1 squared, and then a c over x plus 1. Yeah? And that's putting it in the form that case 2 requires. Yeah? Everybody with me so far? Yeah? Cool. And then it's just doing, once you have this down, then it's just doing the straightforward logical thing, which is to find the A, B, and C, right? That's all you have. So to make the denominator the same, then we need to have the denominator on each one of these individual terms being this thing, right? Which means for this guy, we need to multiply top and bottom by x minus 1, x plus 1. So here we're going to have a x minus 1, x plus 1. Yeah? So I'm going to erase some space. And then here, to have this thing be the denominator of this term, I need to multiply top and bottom by x plus 1. So I'm going to have b x plus 1. And then here, to have the denominator be this thing, I need to multiply the top and bottom by x minus 1 squared. And all of that stuff over x minus 1 squared x plus 1, that thing is the same as that thing. Yeah? And you can just check for yourselves just briefly. If we just look at this A part, then we'll have an x minus 1 cancelling, an x plus 1 cancelling, and we'll just have this. If we look at the B part, we'll have an x plus 1 cancelling, and we'll just have this. If we look at C part, we will have an x minus 1 cancelling, x minus 1 squared cancelling, and we'll just have this. Yeah? So it is indeed the same on both sides. Huh? Cool. So we can multiply by the denominator, and then that will imply that 4x, this polynomial 4x, is the same as the polynomial like this. And let's, in one step, multiply that through. It's a difference of 2 squared, so it's now x squared minus 1, right? Plus b x plus 1 plus c, and let's multiply that guy through. Again, to save time, we're going to have x squared minus 2x plus 1. So this is the equation we extract from being able to put our rational function in this form, right? So this thing right here, okay, which is the thing we have the right to do because we're in case 2, implies this thing right here. And this thing right here is all that we will need to be able to find the coefficients A, B, and C. Yeah? Because even though on the surface it looks like one equation, because this holds true for all x, it's actually 3 equations. It's actually 3 equations, because it's saying that this thing on the right-hand side, which is a quadratic, is equal to this thing on the right-hand side, which is also a quadratic with a 0 x squared term. Yeah? Do you see what I mean? What did we get to? We got to this equation. We had that a of x squared minus 1 plus b of x plus 1 plus c of x minus 1 squared was equal to just 4x. Okay? So, let's write out what that means. So, at this point, the best thing to do is to write this out as a quadratic where you put all the x squared terms first with their coefficients in terms of a, b, and c, then the x term, and then the constant term. Okay? So on the left-hand side, we're going to extract off all the x squared terms. We'll have one from the a, and we'll have one from the c, and then that's the only ones we will see. Yeah? So we're going to have a plus c x squared. Yeah? Then we're going to extract off all the x terms, right? There isn't an x term from the a, right? From the b, there is one. This is a bracket. So we're going to have a b from the x term here. And if we multiply this through, as I did on the other board, we'll have minus 2x, right? So that's going to give us minus 2c. Yeah. And now we put the constant terms. So we get a minus a from here, yeah? And then a b from here, and then a c from here. So we'll have, let's do it like this, b plus c minus a. Yeah? So that is this side, and it has to equal 4x. Yeah? Cool. And then as we saw last time, it's the same procedure. This thing on the left-hand side is a quadratic, right? And so is this thing, but these quadratics have to agree, right? And this quadratic here is a quadratic with no x squared term, right? So it's just this linear, it looks actually higher slope than that. Let's do that better. It's this linear function like this. This is what the right-hand side looks like, yeah? So that's only possible if the x squared term on the left-hand side is 0. The slope here, which is the number in front of the x, has to equal this 4, and the constant has to equal 0. There's no intercept here, yeah? So this thing implies 3 separate equations. So it implies that a plus c is equal to 0, that b minus 2c is equal to 4, and that b plus c minus a is equal to 0. Everybody agree? Everybody happy? Yeah? Let me check that these are my equations. Yes, they are. Good. So then we have to do some stuff to extract out these guys. So I advise you to give these things labels so that you can make note of what you're doing. And then when you check your answers later, you can see that it's being consistent. So we want as quickly as possible to kill off terms of this by scalar multiplying and adding. So what do I want to do? I want to take 1 and I want to add it to 3, because then I'm going to get this b plus 2c, and I'm going to kill the a, right? And this one's a nice equation with b and c, so I'll get 2 nice equations in b and c, right? So my first thing I want to do is take 1 plus 3, and if I do that, I'm going to kill the a, and I'm going to have another c, so I'm going to have b plus 2c is equal to 0. Yeah? So now that's my next equation. I'm going to call that guy 4. Probably these things are very small for you. So on the posted video, you can see these labels on the equations better. Yeah, so that's my 4th equation now from the 1st and the 3rd. Now I want to look at the 2nd and the 4th equation, and I see if I add them, then I'll kill the 2 c's, right? And then I'll just have an equation in b. So then 4 plus 2 will be just 2b, and then we add the right-hand side, so we just have 4. So this implies that b is equal to 2. Yeah, and that's our first thing that we want to discover. Yeah, and now we're in pretty good shape because we have this equation. So it means that 2c equals minus b, which is minus 2. So this implies that c is equal to minus 1. Yeah, and then from this equation, let's put it over here. This implies that a is actually equal to 1 itself. And those are our coefficients. Everybody happy? Yeah? Give me a thumbs up. Do this if something's unclear. Okay, thank you for this question. So this is the same part that we had on Friday, which is we have a polynomial equation here, which looks like it's one equation, but it's not one equation. It's actually 3 equations implicit in this equation. Because when we have 2 polynomials that agree for every x, that's only possible if all the terms agree. So let's do this little aside here. So suppose we have a1 x plus b1 a1 x squared plus b1 x plus c1 is equal to another polynomial. B2 x plus c2. Suppose that's true for every x, yeah? Then that implies that, let's put that as a sentence. Suppose then this implies that a1 equals a2, b1 equals b2, and c1 equals c2, and I'm about to show you why. So consider drawing a picture of these two quadratics, right? So let's draw the first one. Let's say it looks like this, yeah? The fact that we have this equation means that if we draw the second one, it lives in exactly the same graph. So I'm going to do this. So the second one lives on exactly the same thing, yeah? That is in pictures describing what this says, yeah? Then, what does that mean? Well, if we had, for example, a1 was bigger than a2, then for very, very large x, then the quadratics terms dominate everything, right? So all these other terms are negligible in comparison. So it wouldn't be possible that this is equal to this for all x if a1 was bigger than a2, because this guy would just be above the other one, right? So if a1 was 101 and a2 was 100, right? And this was true for all x, and then we put x is 10 billion inside this, yeah? Then we'll have that all the other terms are negligible, so it'll be 101 times 10 billion, which cannot possibly be equal to 100 times 10 billion, right? Do you see what I mean? Yeah? So we must have that a1 is equal to a2, and then we can just kill them. We just subtract these terms from both those sides. Let's take a different color. And then if we compare the next leading order term, now these are actually nice linear equations. They have a slope. If the slope of this guy was not the same as the slope of this guy, then these graphs obviously could not be the same. They would get further and further apart as x gets bigger, yeah? Yeah, so these guys, b1 has to equal to b2, so we can take them away, and then c1 equals c2, yeah? Yeah? They imply separate equations, so we write this as one equation, but it implies separate equations because there's actually lots of information here, because we're saying this is true for all x, so that's the thing that contains more information. So this is the stuff about math being a language that I want to get through. That even though this looks like one equation, what it actually means is something different, because this is true for all x, or strictly speaking for all x, such that the denominator is non-zero, but let's ignore that. So this is true for all x. Okay. So this fact that it's true for all x means that this is not just one equation, it actually contains three equations inside it. The meaning of this contains these three equations. If this geometric explanation isn't working so well for you, just imagine differentiating the left and the right-hand side. So if you differentiated the left-hand side twice and the right-hand side twice, since these things agree for all x, then the second derivative would have to agree, right? And then if you differentiate it twice, you're just going to have 2a1 and 2a2 here. So that would say a1 is equal to a2. Yeah? 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 That is actually the same thing as the picture, but it's just using differentiation rules as opposed to drawing pictures. But it's the same thing. Right? So up here, from the fact we have the equality of all the powers of x on the left and right hand side, we extract off this guy because we extract off this guy because we have the quadratic here has this coefficient. The quadratic on the right hand side is 0 times x squared. So the first equation is a plus c equals 0. And then same for this thing. This thing has to have the same coefficient as the x term on the right hand side. So b minus 2c is 4. And finally, this thing, I'm sure you've got it, I'll just complete it. This thing has to be the same on the right-hand side. We have no constant term on the right-hand side, so this thing has to be 0. Yeah, perfect. Thank you for your question. All right, cool. So we have these 3 equations, did some manipulation, we solved them. Now we can put our original problem, or at least our original rational function that we got from long division, into the form that we want. So we were trying to do this. If we could do this, then we could do the other part as well. This is what we came down to. I think it's +1 like this. All right. And this rational expression here is equal to the coefficients, is equal to this thing that we get from these coefficients we've now figured out. So it's 1 over x minus 1. And then the b is 2, so this is 2 over x minus 1 squared. And then the c is -1, so -1 over the other term, which was x plus 1 dx. That is what we now have as a result of doing this stuff. Okay? Yeah, because what this algebra just told us is that this thing can be written like this thing. That's how we started on the other board, right? Yeah? Because that algebraic form said that we could write this in the form of some A, some B, and some C here. Yeah? You see what I mean? So this was the A here, this was the B, and this was the C on the top. Yeah? Give me a thumbs up if you're with me now. Do this if you're not. Do this if you're not. Okay, good. So, okay. Is it a 4 on top of the fraction? Yeah, it's a 4, I think. No, it's a 4x, thank you. It's a 4x, thank you. Yes, of course, because that's how we got the equation, this guy, thank you. That's how we got this guy. All right, cool. So this is our guy. This is the thing we have to integrate. And I claim that we can do this, right? Because all of these terms are things we can handle. So help me out here. What is the antiderivative of this first term right here? Come on. What's the antiderivative of this first term? Yep. Log of the absolute value of x minus. Yep. I already put it. Yep. All right. Next term. What about this one? What's the antiderivative of this thing? Yep. Minus 2 of x minus 1 to the minus 1. If we differentiate this, the minus 1 comes down, and then we lower the power, so we get x to the minus 2, and we differentiate the inside, we just get 1. So this thing is the right thing. And this guy, you guys know as well. And then we just have plus constant c, and that's it. That's it for this part. But we're not quite finished, because our original problem was this terrible expression, x to the 4 minus 2x squared plus 4x plus 1 over x to the 3 minus x squared minus x plus 1. And we found by long division that this was the same as x plus 1 plus this other thing, which I'm just going to put, let me just write it like this. It's the same as x plus 1 plus the stuff in the red box. Okay, this red box. Okay, dx. Because by long division, this expression was x plus 1 plus the stuff in the red box, yeah? And therefore, to actually get the final answer, we have to integrate everything. But now this is easy. We know the integration of this, x squared over 2 plus x. And now we put all of that stuff together with this stuff. log of x minus 1 minus 2 x minus 1 to the minus 1 minus log of x plus 1 plus constant c, and that's it. We are there. Okay, cool. All right, let's recap the steps. Okay, first step, we saw this thing wasn't proper. So we did long division to get it into the sum of just a polynomial plus this proper rational function. Good. This proper rational function, we messed around with this guy. We had to understand what form it was in. And we found that this thing we could factor as x minus 1, x squared minus 1. If you multiply out these terms, you can see that you get what you need. You're going to have a x to the 3, a minus x squared, and then you have a minus x and a plus 1. So this is clearly the right thing. Yeah? This thing we further manipulate to be x minus 1 squared x plus 1, and now we see we're in the territory of case 2. Repeated linear factors. Yeah? Then we write it in the correct form. So we need 2 coefficients to deal with this x minus 1, right? And then once we have it in the correct form, we make the denominator the same. Yeah? And then we multiply through to get rid of the denominator. So we just have the numerator is equal. Yeah? And that is the statement we have here. The numerator is equal. Yeah? And then we understand the numerator by writing it out as a polynomial with the coefficients in front of all the powers of x. Right? The coefficient in front of the x squared, coefficient in front of the x, the constant term. And then this thing implies however many equations there are. This thing implies however many equations there are depending on the highest degree in this equation. So now our highest degree plus 1. The degree here is 2, so the quadratic terms agree, the linear terms and the constant terms agree. Yeah? So a polynomial equation like this contains other equations. They contain a number of equations. If the highest degree is whatever n, then it contains n plus 1 equations. Okay? So in this case 2, it contains 3 equations. And we extract off these equations by comparing these highest powers and the second highest and so on. Extract off the 3 equations, we solve for them, put the coefficients in, and now we have that this thing, intractable problem, becomes this thing, straightforward problem. So the only thing different than what we did on Friday was that we did a different form to start off with. Yeah? We did a different form. So you have to just remember this case 2 form, that when you've ever repeated linear factor, then you have to deal with it by putting in 2 coefficients. You have to do this, and you have to do another guy like this to handle it. And then this guy has just got 1 power on it, so we just need 1 coefficient to handle that. So the only extra wrinkle in this machine is just knowing to put it into this form. Yeah? So if you got good at doing case 1, case 2 is very, very similar. There's only one other thing to handle. Are you with me? Okay, I'm going to raise the board, and then we're gonna do some other stuff. So, well, not other stuff, but we're going to keep talking about this. But we're going to move on to a harder case. So do this if anything's unclear before I erase. Okay, looks like we are all on the same page. If you can do case 1, you can do case 1, 2, 3, and 4 for sure. So don't be concerned that this is a particularly difficult topic. This is not. This is just an algorithm. It's a lengthy algorithm, but it's just an algorithm. Okay, let's talk about it. Case 3. I'll wait for time. Case 3. How shall we say this? Contains Q, contains irreducible don't think that's how you spell irreducible. Irreducible factors, that's i.e. can't be factored into linear terms. So what does that mean? That means that Q will have an expression of the form, will have a factor of the form of a quadratic ax squared plus bx plus c. But this quadratic is not the one that we can actually factor, right? So what conditions on a, b, and c do we have so that it cannot be factored? When do we fail to be able to factor a quadratic? Yeah. Hussein, don't tell anyone what delta is. Tell me in terms of a, b, and c. Someone else. Yeah. So if b squared minus 4ac is less than 0, yeah, that means we cannot find the roots, right, with this formula, yeah? Better to think about it this way. When this is true, it means the quadratic is not actually crossing the axis, right? So there are no roots, yeah? And then we can't factor it, yeah? Or we can't factor it with real numbers, yeah? Then we cannot factor. Do you remember this stuff, right? Because if we have this is bigger than 0, then we have two roots, and then we can write x minus one of the roots times x minus the other root, and that thing is the same as the quadratic. Okay, good. Everybody happy? Yeah? All right, so in this case, we have to introduce two coefficients like this. We're going to have to write ax plus, let's write different letters. We're going to have to write capital AX plus capital B. Yeah, over this quadratic. And then we have to put this thing in the mix to deal with this irreducible quadratic. So everything else will be the same, except we have to stick this guy inside as well. Okay, so if we have, let me do an example. If we have something like this, suppose we have x minus 2, x squared plus 1, x squared plus 4. Okay? All right, so this is a quadratic. This guy cannot be factorized, right? We just see this thing lives above the x-axis, yeah? It's never less than 2. Sorry, it's never less than 1, right? It's always above 1. This guy is never less than 4. It's always bigger than 4, big equal to 4, right? So neither of these guys can be factored, yeah? Yeah? This guy is a nice linear form. So for the linear form, then we can just put this, say, a over x minus 2. And now to deal with these guys, we have to write them in this form. So let's do cx plus b over the first irreducible quadratic, like this. And then for this guy, another couple of coefficients. Let's do dx plus a, b, c, d, e. That is the form that we have the right to put this in. And again, this is an algebraic fact. I can't explain to you why. It's just true. We are given it, and we use it. Okay. So whenever we have something which involves irreducible quadratics, we can still break the thing up into something like this. Okay. But now we don't put just one coefficient above the thing. Now we have to have a cx plus b and a dx plus e, just like this thing, yeah, tells us to do. That's the extra subtlety. That's the extra thing that we have to do. Yeah. Cool. So I've just been reminded that class is actually just finished, but I want to keep going and do another example of this so that we can wrap this topic up. So if you have to go, just go, and everyone else wants to stay, just stay. And I will post a video of this where you can look at this final example that we will study. In the case 4, we won't do an example, but it's exactly the same. Case 4 is the rarest case, so you'll see it the least often, but it's the same thing. In every case, it's the same thing. It's knowing the form and then just finding the coefficients. Okay, let's do an example of case 3. This is our example. Okay, let's look at this. So, if we look at the bottom, then we have x to the 3 plus 4x. Factor out an x, we have x squared plus 4. Then this thing is clearly irreducible quadratic. There's nothing we can do with that, right? Can't factor it. This guy is always bigger than 4, so it doesn't cross the x-axis. There are no roots. We have to use case 3 here. Yeah? So, in the situation of case 3, so need case 3. And let's just do it. So we need to write this thing over x to the 3 plus 4x. And we have one linear factor. Let's write this a over x. And then this bx plus c to handle this guy. Okay. And then we need to make the common denominator. So we're going to make this thing plus 4 like this. And then this thing, we're just going to multiply it all by x. I'm going a little bit faster because we've lost most people, I guess. Yeah, that's what we have. Yeah, same deal. And then this implies that the top over here, 2x squared minus x plus 4, is equal to this thing here. And we're going to write out in one go in terms of ordering the coefficient from the x squared in front of the x in front of the constant as before. So let's pick out the x squared coefficient. We have 1 from here, we have 1 from here. So we're going to have a plus b x squared. Yeah. Let's pick out the x coefficient. Nothing from here, and we have just cx from here. Yeah. So we're going to have c times x right here. Yeah. And let's pick out the constant term. So we're going to have an 4a from here, and we're just going to have nothing from here. So the only constant term is this plus 4a. So this is the polynomial equation that we extract from here. And as always, this is true for all x. Yeah? Everybody with me? Give me a thumbs up. All right, cool. So this is what we have. This is our polynomial equation. It's a quadratic on the left and the right. So that means we have 3 equations that we extract out. We extract out the equation comparing the x squared term. So we're going to have 2 is equal to a plus b. So 2 equals a plus b. Comparing the x, we have minus 1 is just equal to c. So that's easy. So c equals minus 1. And comparing the constant term, we're going to have the 4 is equal to 4a, so that's easy too. So we know that a is equal to 1, and then c is equal to minus 1, and then b will have to also equal to 1. So we have our coefficients. In this case, finding the coefficients is really easy for us. Yeah? So then this thing over here, let's put this in a box. This thing in the red box becomes 1 over x and plus x minus 1 over x squared plus 4. That's better. X squared plus 4. Yeah? Cool. So then we can integrate. Well, we can integrate some of this stuff pretty easily, right? So we can write this as 1 over x plus x over x squared plus 4, and then minus 1 over x squared plus 4. Yeah? So this guy is easy. This guy I claim is easy. How do we know that we can do this guy? What method do we use for this? Just a u sub, right? It's an easy u sub. We let u be the bottom. We'll get this x dx from differentiating u, and then it's all set, right? So this is an easy u sub. This guy, what form was this guy? What methods do we have that would help for this guy? No. This guy here, the last guy. Yeah, yeah, we can do something with arctangent indeed, because I see. So when whoever that was said u sub, then that might have been what you were thinking. So yeah, apologies if I too quickly dismissed that. Indeed, we know that. Let's put it over here. That if we differentiate d by dx of arctan, you learnt this in the implicit differentiation section. This turns out to be 1 over 1 plus x squared, right? Which isn't exactly of the form we want here, but we can do some messing around, right? So we could write this as 1 over x squared plus 4. Let's write this as 1 over 4 x over 2 squared plus 1, right? And then if we did the u sub, replacing x by x, letting u be x over 2, then we would be in the form that we wanted to. So let's do this, x over 2. So let's write u equals x over 2. So then du equals dx over 2. So then if we integrate this thing, integral of 1 over x squared plus 4 dx, then that thing will be the same as 2. And we factored out this thing over 4, the integral of 1 over u squared du, which goes 1 over 2 arctan of u. So I realize my writing is getting really small here, but I'm trying to avoid erasing the board before I have the answer. So this is 1 over 2 arctan of x over 2. So we can indeed handle this guy too. Yeah? So we can do this whole thing. So this guy right here is going to be, let's just integrate stuff over here. I'm going to have log of x like this. This guy, if we do the u sub, let's do it in our heads. Let's let u be this thing. Well, okay, let's just do it in our heads by differentiating log of x squared plus 4. If we do that, we're going to have 2x over x squared plus 4, which isn't quite what we want. So let's just get rid of the 2 by putting a half here. Log of x squared plus 4. And then this guy we've just figured out, it's this thing, minus 1 over 2 arctan of x over 2. And then plus constant c, and that is our answer. Okay? So not particularly hard. Yeah? Okay. I have a final thing to say, and that's to tell you the form of case 4. We won't actually calculate one. I'll just tell you the form, and then we'll be done for today. So again, stick around if you still have time. Final case. Case 4. Repeated irreducible factors. Okay, so that's when we have quadratics that we can't reduce. So there'll be something in the form ax plus b, ax squared plus bx plus c. But then there'll be some power, like r. Okay? Then we have to introduce the following terms. We're going to have to write a1x plus b1, and then the quadratic to the power 1 plus a2x plus b2, and then the quadratic to the power 2, and so on until we have arx plus br, and then the quadratic to the power, this is squared, quadratic to the power r. So it's completely analogous to case 2, right? When we had case 2, when we had a repeated linear factor, we had to have as many coefficients as the number of times it was repeated, the power of the repetition, right? And when we put it coefficient over the first power, coefficient over the second power, and so on. Yeah? But now we have an irreducible quadratic, so every irreducible, we have to introduce this ax plus b in capitals, right? But then we have to keep doing this until we exhaust the power of the irreducible quadratic. So it looks, again, like another very complicated thing, but it's very similar to case 2, right? So it's not without kind of a symmetry that makes it easier to remember. And this is the rarest case. So if this has come up in an exam in the last 8 or whatever years, I don't remember it because this is the most obscure form, but it's not impossible. It's not impossible that it will come up. So I'd rather you'd know it, and it's not particularly difficult to get this clear in your mind, because once you have this, then you can do case 4 as well, and it's the same procedure. So we're not going to complete an example of this, but we're just going to do the decomposition of some example, and then everything else is identical. So if we have this guy, and it's given already to us in this nice form, so we see it's already factored. Okay, so let's identify what we have going on here. So this quadratic here, if you take b squared minus 4ac, it's definitely less than 0, right? It's minus 3. So this thing can't be factored. This is an irreducible quadratic. X squared plus 1 is obviously irreducible. It's always above or equal to 1, right? No root, so this is irreducible. So what do we have? We have a linear and a linear. So these are two linear. This is an irreducible quadratic to the power 1. This is an irreducible quadratic to the power 3. Yeah? We're going to put all of these pieces in our decomposition using all of our rules that we know. So for the linear term, let's just do a over x. That deals with that guy, nothing else to worry about. Well, I should have also said that this is clearly proper because the degree on the top is 6 plus 2 plus 2. So it's 10. The degree on the bottom is 10, the degree on top is 3, so definitely proper. So we can do this stuff. We can put this into the forms that we know. So deal with this guy, just a over x. To deal with the next term, we have a b over x minus 1. That's easy. This guy is an irreducible quadratic. It just occurs once. So let's write that as cx plus d over this guy. And then this guy is our irreducible quadratic to the power 3. So we have to put all these different coefficients in front. So let's do the first one. Let's call it e1x plus f over this thing to the first power, x squared plus 1. Then let's do this with f1 here. e2x plus f2. And now to the second power, x squared plus 1 squared. And then finally, e3x plus f3, this thing, to the third power. Oops, x squared plus 1 to the power 3. And that's it. That's it. That's using this form to handle this irreducible quadratic. Okay? And once we're in this stage, then it's exactly the same as before. We will make a common denominator, yeah? And then we'll have an equation on the top, yeah? Which will be a cubic equation on the left-hand side equals this thing on the right-hand side, yeah? So we will have a whole bunch of equations. So this thing will have many, like on the right-hand side, when we make a common denominator, the numerator will be some high-level polynomial, but most of the coefficients will cancel because you only start having coefficients at 3 and here at 1 and are a constant term. So we'll have this many equations that will come out from this, and then we'll solve them, and we would be able to find all the coefficients and actually integrate this thing. So one of the reasons we don't often see case 3 is that you can see you get many coefficients, it gets pretty complicated, and there's a limit to how much we can expect you to solve simultaneous equations at this stage, having not done linear algebra. So that's one of the reasons it's rare. So if you do see case 4, it'll be a rather simple manifestation of case 4. It's unlikely you have the quadratic repeated more than once. So don't be scared about having to solve a very complicated linear system. You're not going to encounter that. It's not part of this course. That's another course. So yeah, you'll need to know this form. Perhaps you'll have a question asking you to do this. Just put it in the right form, but not actually to evaluate it. But you're not going to be doing a very long, complicated thing to find many coefficients. So don't be put off by the way this looks. All right, that's the final case. So with this case, we can do all of the rational functions we have to do. Okay, every rational function. If you mess around with the denominator, you will factor it as much as possible. You'll identify the distinct linear forms, the things that can't be put into linear forms would remain as quadratics. And then you'll be able to put it in this form and then just solve it the way we've done before. Okay? This is lengthy, but this is not difficult. This is just following a straight line. Once in this form, you just take one step in front of the other until you come out with the answer. Nothing really to think about except to not make a mistake in your algebra. Yeah? All right. How are you people feeling? Feeling okay? Yeah? All right. Any final questions, Go ahead. Everybody okay? All right, I have office hour now, so stick around if you have any questions. Otherwise, goodbye, and see you on Wednesday.